Hello and welcome to the exida webinar, Functional Safety Management Planning Part 3. Take a minute to check your setup. Audio is being provided via the internet, so you want to make sure your speakers are enabled in all places and that you can hear me. And your microphones should be muted so that we don't have any sound coming in and interrupting the webinar. If you have any questions as I'm going through the slides, there is a questions tab in the control panel at the top of your screen. Please use this to type in any of the questions you have at any time throughout the webinar, and I will respond to those questions at the end. A recording of the session will be made available to you via email probably tomorrow, and it will be posted on the exida website for anybody who wants to go pick it up there later. All right, let's go ahead and get started. This is part 3 of a 3-part series on functional safety management planning. We'll be focusing on the implementation operation phases of the life cycle and maintenance activities, decommissioning, etc. My name is Denise Chastain-Knight. I am a chemical engineer. I've had more than 31 years engineering experience working in a wide range of processes. I've worked both on the operations side and on the design and consulting side. And I've had the opportunity to be exposed to a large variety of different chemical processes and see what is similar between them and what's different. I represent exida at the Center for Chemical Process Safety Technical Steering Committee. And then I'm past chair of the Body of Knowledge Development Committee for AICHE and also a past chair for the PE Exam Development Committee. Runaway slides there. Okay, just kind of a reminder of the safety life cycle. This 3-part series has been based around looking at the different aspects for planning that are a requirement of the safety life cycle. In part 1, we focused on setting up just a basic structure, doing the high-level planning documents and looking at all the procedures and processes that would go with to support that policy-level plan, and a structure in which we might do that. In part 2, we focused on just defining what are some of the requirements that you need to plan for in the analysis and design phase of the safety life cycle. And we looked at some of the trip points that people experience along the way because they may not have had sufficient planning around that. In part 3, we're going to look at the implementation, validation, and the operation phase and the verification activities that go along with that and the planning activities. And again, we'll look at some of the trip points where planning earlier on in the process may avert issues at these later phases. If you have missed any of the other earlier webinars, part 1 and part 2, you can retrieve those at exida.com/webinars. They are both posted, part 1 and part 2, and then part 3 will be posted probably sometime tomorrow. So we invite you to utilize that. We'll focus on these clauses for the functional safety management planning. We'll go back a little bit to clause 5, one particular element of it that refers to this implementation and monitoring activities. We'll talk about verification throughout these later phases of the life cycle and then look at some of the specific requirements from the clauses and the balance of the life cycle phases. Our goal is to ensure prompt follow-up and satisfactory resolution. Those are key words, and we're looking at what we want for monitoring through the implementation and monitoring phase. This is the part of the life cycle where a safety instrument and system spends most of its life during operation. It's after we've turned it on, and we have to maintain it and make sure it stays robust in order to assure that the risk reduction is actually achieved. These life cycle activities that we're needing to follow up and maybe work through from at this phase include your process hazard analysis, risk assessment, auditing, verification, validation, functional safety assessment, and then of course any post-incident activities that we have. The standards have been out for a couple years now, and there's a new version of IEC 61511 that came out in 2016, and it has placed additional requirements on the supplier responsibilities and the compliance that they need to have. So if you're using suppliers to provide either products or services through any part of your implementation of your life cycle plan, then we need to make sure that they meet the appropriate criteria. So you're looking for performance evaluation of those suppliers to make sure, what systematic failures do their processes introduce into the system. Is their performance and their methods consistent with the policy and the plan for your organization? And then is there monitoring for things like demand rate and failure rates? And then, of course, what corrective actions are taken to resolve any deficiencies? If something is failed or there's deficiencies, then it's repeatable. And if something's not available, then it's not going to be reliable and meet our targets. In the new version of IEC 61511, they've actually beefed up the instruction a little bit, and this is the actual language out of the standard that you're seeing on the slide for implementation and monitoring planning. When they refer to everything should be operating in a safe manner, what that means is no dangerous failures within 12 months. And this is a new version of IE 61511. In the US, a lot of folks may be using ISA 84, which is currently based on version 1 of 61511. But it is anticipated that IS 84 in their next revision will adopt the 2016 version in total. In the older version, or in the current version of ISA 84, there is a statement of a grandfather clause. The language that previously appeared in 61511 was a little bit soft about that. So a lot of people did do grandfathering. But when this is removed from the ISA 84 clause, then obviously it means we need to implement these procedures and practices on all systems, not even if they had been pre-existing prior to the issue of the standard. In part 2, we saw this slide previously. It was just kind of a list of what's required for the verification activities. Basically, we are doing verification throughout the entire life cycle, but when we go into, before we go into the implementation phase is where we actually do a validation, and that is a little bit different than a verification. There's a little more requirements there with it. But as we're going through the life cycle, we're looking at all these different things that need to be verified. We should, at each stage of the life cycle, be completing those verifications, and there ought to be criteria for what is acceptable verification to move forward into the next stage. When we talked about these in part 1, we just went over what are the requirements. Today we're actually going to look at some of the issues that might trip up a team in the process and maybe end up forcing them to back up into the life cycle to do rework or address shortfalls. And then, of course, if you're working and putting a plan together, you will want to look to the new requirements in the 2016 version of IEC 61511, because in that new version there's some more specific requirements for what should be addressed. As we're doing SIL verification, we need to have in our plan an approach for addressing these items here. We talked a lot about the methodology in part 2. So today we'll concentrate on some of these other approaches. For a probability of failure, there's basically 2 metrics that we're looking for to target. Probability of failure on demand average is for a low demand operation, and probability of failure per hour would be for a high demand or a continuous mode of operation. This is effectively the measure of what is the random failure potential associated with your safety function. Random failures are usually associated with the degradation of mechanisms in the hardware, and they occur at an unpredictable time, but with sufficient data we can interpret interpret data or predictable rates from this information. Random is inherent to the system and cannot be eliminated. That's not to say you can't change it. By having a good plan and an approach for looking for robust failure information and picking devices that have robust or lower failure rate data, you can reduce the failure rate in your overall system, but there is always going to be some random failure potential. The second of the compliance trilogy is the hardware fault tolerance. It's often called architectural constraints. In essence, this is a measure of the redundancy of the systems, the redundancy that is required. And there's two routes to looking at the hardware fault tolerance. Route H1 or 1H is where the tables come from IEC 61508. They look at the safe failure fraction because they're based on safe failure concepts. So we look at the safe failure fraction of a given component, and then by comparing that in these tables with what our SIL target is, it tells us what our redundancy needs to be. So for example, if we have a transmitter that has a 60 to up to 90% safe fail fraction, and it's in a SIL 1 application, it's perfectly fine to do that in a single architecture. Our hardware fault tolerance is 0. We do not need any redundancy. The same device, if we were trying to apply it in a SIL 3 application, we need a hardware fault tolerance of 2, or 2 layers of redundancy, which would be 3 devices. IEC 61511 and ISA 84 have the tables for the 2H route, which is based on reliability. And this particular chart is from the newer version because it's a little different than what was in Rev 1, Edition 1. And it looks also at the demand mode, whether it's low or high of the individual device, but it does not consider safe fail fraction. So your functional safety management plan needs to look at how you want to define these architectural constraints, which rule set do we want, and make sure that the requirements are well defined in the plan and in the procedures that support the plan, so that anyone who's working on doing your verification knows which to choose. The third part of the compliance trilogy is the systematic capability. This, in essence, are the types of errors or failures that can come about through systematic activities, being it design, testing, procedural related, people related. It's the kinds of things that are not about the device, they're about how you're managing the device. Systematic failures can be eliminated after they're detected with a good rigorous type system, and of course you have to have means in place to recognize those. So really when you're talking about systematic capability, think about the 3 Ps. Personnel, what is their training and their competency? Procedures, are they written? Are they correct? Are they followed? Are they understandable? And of course your paperwork. There has to be a documentation process that enables you to capture information that might reveal systematic faults throughout the process. And this is true at the manufacturer level for certified devices or for the devices, and it's true at the operating, testing, maintenance level during the operating phase. Systematic failures are a function not only of the system but also of a particular condition around that system. So there's a lot that needs to be controlled here. And they can be eliminated. So this is another place where you can improve reliability through discipline. Okay, now that we know what our targets are, we go into the we ask, okay, I have to do verification. That's a very data-driven activity, and the ISA standard says that the information, we need to list the information in which verification is to be carried out. Well, where do we go get that information? IEC 61511, Edition 2, has added some requirements for more than just identifying that information, and it's setting some quality standards on it concerning the correctness, completeness, and the whole pedigree of the data trail, and is it auditable from a documentation standpoint. Again, because we anticipate ISA 84 will adopt this, this is going to be a part of the standard in the future for ISA 84 as well. And it's important to make sure that we are using the correct data for calculations, because it can, if we have incorrect data, it can either result in a costly over-design, but much more frequently we end up with optimistic information that would result in an unsafe or under-designed system. So we have to define in our plan up front what is our criteria for acceptance of data to make sure that the right information has been used as the basis for our design. Or we end up reworking when we discover that at validation. Failure rate data, there's certainly a lot of documentation out there for failure rate data on random devices. And we also need to look at what is the systematic capability, and that usually takes individual studies and assessments of the actual manufacturing process of specific devices, where failure rate data for the random part may be pulled from a lot of sources. The important thing in, accepting the failure rate data are these three elements. It has to represent the useful life of the product. It has to consider the entire population. If it's only based on if some devices are thrown out selectively, it may not be representative. And then it has to have a statistically valid data set, enough data pulled together so that the calculations or the averages done on it are, again, representative and not skewed, because a small data set will skew. When you're recording information, as you're making collection of data for building one of these databases, one should consider all failures random until proven otherwise, so that they can be recorded as faults. We talk about useful life. This is an important parameter not only from determining is your data set valid, but looking at your overall mission time for the process. How we come about determining the useful life of an individual product is shown in this graph here. The little squiggly line is actual raw data tracking failures over a period of time for whatever widget this data is representative. The bathtub curve is kind of a smoothing showing a period at the beginning where we have got infinite mortality. There's early wear out, usually manufacturing defects. Some things do fail in the very early days of use. And then on the right-hand side, we're seeing wear out. As things have run for a longer period of time, you start seeing an increased rate of failure as the devices wear out. And the red line is kind of the box we're using to approximate, and the horizontal, a appropriately conservative constant failure rate for a given device. And then we are making the useful life to stay within that bathtub curve, because the idea of predicting a constant failure rate on out past the wear out point, that it's not meaningful beyond that point. So this brings us to the question that I mentioned earlier on the no more grandfathering allowance. When we start looking at the useful life of the devices, typically on sensors and transmitters, they're highly electronic type devices. So while there are a few that have been qualified to a much longer useful life, most tend to run in the 10-year range. And it's, for fire and gas detection or some of this more sensitive equipment, it can be an even much shorter lifespan than that. For devices that are often used in input and output interfaces, relays, amplifiers, things like that are pretty simple, often as much mechanical as electronic, they can have much longer life in some cases, but again, there's a lot of those that may run in the 10 to 20-year range. As were the logic solvers, most logic solvers, about 10 years is a typical useful life. Again, there's a few that are qualified for higher length of useful time. And then in the final elements, that's really our weak point in this for setting our timeline, is the solenoids, valves, actuators do tend to have a much shorter useful life. They do wear out. You can see solenoids even down some in the 3-year range. So your procedures not only need to have guidance for selecting these devices, for looking at their useful life appropriate early in the process, you may want to set up some kind of procedures where some of these things like valves are being rebuilt much more often. So if you want to have mission times over a 10-year time frame, because so many components have a useful life of 10 years, there is required a very deliberate selection to get the devices that are going to give you an adequate useful life to support that longer mission time. And it's got to be a cost balance as to whether you try and pick and choose and get just that minority that's going to give you a much longer mission time, or live with a shorter mission time and set up your maintenance and testing plan appropriately. When we're getting data sources for doing our calculations, one source that we can look to, of course, is B10 cycling testing. Then there's some data collections out there. The Offshore Reliability Database is one example of a large pool of data where the devices were used in a harsh type environment or conditions. There are a lot of sources, so how do you know what is the good one and what is going to be fit for purpose? I just added the exida SERH, which has gone out and looked at a lot of those databases, pulled in that information, compiled additional FMEDA information into it. It's a good data source that's looked at a lot of this and has done some assessment, already pulled together for you what is fit for purpose in a safety instrumented system. So that is one resource that folks can use. If you want to do FMEDA analysis, those are typically done on individual devices, and that activity is actually a predictive failure modeling tool that is calibrated to actual component failure history from databases. So it's a good way of sorting out, if you don't have any other approach for getting data, certainly an FMEDA is one way to look at specific components. And then, of course, there's a lot of components that are certified for use in SIL environments. So we can look to those certificates, but how do we know that the certificates meet all the criteria? And we'll talk about that in a minute. The B10 failure rate data does assume wear out. All the failures are due to premature wear out and does not consider infrequent modes of failure. When we're talking the chemical process industry, the devices are not moving. The demands are low, so our valves may sit for some period of time before they are asked to move. So issues like stiction, cold welding, corrosion, all of these other things that are not wear out failures but functions of being idle, those become much more significant, and they are dangerous failures. So for that reason, B10 data is generally not applicable in the process industry applications. There's occasions where it's appropriate, but for the most case, it's not the best approach. If we're looking to certificates to say, okay, I'm just going to go certified components, let me go find out what's out there, we need to kind of vet those certificates because there's a lot of documentation out in the general population that may not meet all of the criteria for SIL certified. So your plans and procedures need to have tools and techniques within them to help the users vet these certificates so that your designs end up being based on certificates that you know meet all of the requirements, or you understand what's missing from the others, from other documentation that might be presented, what needs to be augmented. This is one example. We're going to go through a couple things here for how to determine if the appropriate standard. We've got two items here that came off of certificates. They're both looking to the same IEC 61508 standard, which is what components, the actual devices, should be certified to. And they're the same edition. However, one of them has 7 parts of the standard listed, where the other one is just looking at one part. Now, you'd really have to dig into the standard quite a bit to pardon me. You have to dig into the standard a little bit to know the details of what's being done in each of those parts. But clearly, one of these is questionable if it's as we I'm sorry. We also want to obtain and review the supporting reports. Pardon me, hold on a minute. I'm going to pause just 1 second. Okay, I think I got that tickle cleared from my throat. We want to obtain the and review these supporting reports. So each of the certificates should actually have a list of documents that are a mandatory part of the certification. I should expect to see an assessment report, and there should be a safety manual for each of those devices. Get these documents before procuring the instrumentation, because it will not only qualify what is the basis for the certification, but it will also give you important information on how that certification was done, what the assumptions were used in that certification process, in the calculations, the methods and techniques. The safety manual is going to outline for you maybe one or more proof test procedures and what proof test coverage would come with that, as well as a lot of other information that's very important to proof test development and making the plans for the operating phase of the life cycle. So these documents need to be required up front so that we know the devices that are going into the system and the procedures and practices we're developing to support them in the operating phase of the life cycle are robust. When we're looking at the certificate, okay, maybe we found all these other things are there. When we look at the source of the data, the methodology we discussed for doing the verification calculations, there is a term in there, lambda DU, which stands for lambda dangerous undetected failures. There's a couple flags on this particular line item. Note they say dangerous undiagnosed failures, so you really have to understand what are they lumping into, or what is the developer of the certificate lumping into that lambda DU number. Undiagnosed suggests that maybe there's failures that were not detected, or failures that once they have been diagnosed, they maybe pulled them out of this and called them something else. So it's important to understand if there's a difference in definition. And the other note is we've got from return data. There's a lot of valid use for return data, but you have to understand where it came from, how it used, and what the basis was. So when we look at these kinds of things and they raise a little flag, then I'll ask the question, well, is the data reasonable? This certificate is reporting a 5 FITs failure rate, and a FIT, of course, is failures per 10 to the 9th, or failures per billion hours. So is it reasonable, and how do you know that? Well, silsafedata.com is one place that you can is the place that you can go to for a number of devices and look at what are the typical failure rates from billions of hours of operating data. These bounds have been pulled together. And in this particular case, when we see a typical range would be between 60 and 400 FITs, and they're reporting 5, that's, I would be likely to flag this certificate as unacceptable, because it's telling me there's something in the data or in how the data has been managed that maybe there's failures that are not being accounted for in that number. And using this number in our calculations could result in a design that does not meet your risk reduction requirements, but the numbers would tell you it did in the calculation. So it would end up with an overly optimistic design. Now, field return studies, as I said, there's pluses and minuses associated with it. It's always great to have real data, but you have to understand the calculation methods that are used in analyzing that data to make sure it meets the requirements for why we want it, the data for SIL verification. one of the big catches there is that we don't actually know what percentage of actual failures are returned. Like in the example I gave you before, that was a solenoid valve. Solenoids are inexpensive, so it's likely that a lot of them are simply just disposed of and replaced without ever being returned to vendor. So it could very well be that there is a shortage in the information. And there are different definitions of failure, as I pointed out on that previous slide. When the calculations are being done, it's important to have the operational hours match up to the actual sample set, and sometimes we will see that the operational hours are based on shipping records. So if only some of the failures are being counted for when devices are returned, and others are just being thrown away without the return data reflecting what happened, but the operational hours are based on all shipping, that can again lead to a very low failure rate coming out of this kind of study if it's not adjusted for the ones that are not being returned. All certificates for SIL certification should be done by a certified credentialed body. So if they're not, we put these in a category we call house certificates. And some of the things you might see on the house certificate, they'd be called a certificate of conformity, or if they are produced by a manufacturer or a third party that is not accredited for SIL certification. So how do we know what people are accredited for? Well, you're going to see if a certified body is accredited, they will be able to show the accreditation body logo on their certificate. And we've got some examples here in the pictures. And effectively what's occurring in that case is the accreditation body is coming in, they're looking at how the certification body is doing the work, what standard they're required to, what procedures and practices and checks and balances are in place, and what discipline the organization has for following their quality control of staying on track with the process as it's defined. And the accreditation body will say, yes, they do this according to all of the procedures. So if you don't see the accreditation body on their certificate, that should be a little bit concerning. And certainly if it's not there, you would encourage the certification body should also have evidence of their accreditation certificates on their website. And they need to be certified under the ISO IEC 17025 and the ISO IEC 17065 requirements for doing SIL certification, or doing devices that are going to be used in SIL certification. So definitely go out and look at, you're receiving certificates. You want to go out and you want to do this scrubbing and locate the accreditation body, and your plan and procedures ought to have guidelines in there for people to do this. This next one is just an example of a certificate. This is certainly a qualified certification body in some locations, but not all locations are actually accredited to do the SIL verification. So in this particular example, you'll notice there's no accreditation body logo on the certificate. So look for that kind of thing. And not all devices are going to be SIL certified. There's a lot that need to go through the proven in use process. So when you're trying to develop a proven in use process, if you've got some history and operating experience, you can go back to the old history there and try and develop it, but you're also going to have to get some operator or input from the original equipment manufacturer, and this can be a timely and consuming and costly approach. In some cases, instruments may be put in and you end up developing some of the support for this proven in use over a period of time. And we'll talk about I've got a couple slides later, we'll talk about how you might be able to start collecting all of this information. Diagnostics is one of the items that we look at from verification that can help us improve the safety and availability of equipments. Diagnostic coverage can vary widely depending on what the diagnostics are and what that capability is. If we're looking at reference diagnostics, then that basically is the kind of diagnostic tool where one device is checking against baseline predetermined characteristics, such as voltage, timing, and signal sequence. For comparison diagnostics, this would actually be comparing device in your safety instrumented system with a device that measures the same process variable in another location, maybe out of your BPCS or out of vendor package unit. And it uses a little different techniques, but depending on how it's set up, the diagnostic coverage you're going to get is going to be continuously monitoring it. Now, this is not the same as the faults that are detected by our proof test coverage. These are failures of dangerous failures that can be detected while we're on stream, and the real advantage of that is you can identify those failures and you can get them corrected immediately instead of running in a failed state for the period of time between proof tests. And of course, partial valve stroke testing is another useful diagnostic for final elements, but our plan needs to indicate if we want to use these, what the requirements would be for setting up, how to do the diagnostics to get the right testing approach that you want. And certainly if you're doing partial valve stroke testing, that needs to be planned in advance and is only suitable in processes where it won't actually cause the process upset. There's a testing approach also to the verification. A lot of what has been done up to the implementation phase has been theoretical verification against the calculations, against the data, against all the supporting input information. But it's very important to do this testing activity as you're going into the implementation phase, to look at the various criteria, not only of the hardware and devices, the logic solver. There will be a factory acceptance test. There ought to be a site acceptance test and a site integration test that goes with that. The field devices need to be exercised and tested in a number of ways to assure their integrity, and that's not just calibration and continuity testing. There ought to be full proof tests that go with it. So this verification testing is a very important part of the validation activities. So the plan needs to define what's expected in terms of the plan or the procedure, depending on how you approach it. Your construction management plan certainly needs to look at all of the testing and going into the commissioning, because there will be activities that's a basic construction testing that should be done by the contractors or the construction team. But then there's also the acceptance team that the owner and operator team is going to want to look at. So things such as, double checking the grounding and the calibration. Bench calibration is good. Field calibration is what we want to accept on. And how do we to resolve any non-conformances that are found, because this is a transition period where we're getting ready for handover, and obviously the owner acceptance team is not going to want to accept the process until they're very comfortable that this has been met. These activities need to be tightly coordinated within the project schedule in order to assure that they all get done and get done in the right way. And in most cases, this is going to be typically your first application of the full proof test, making sure that it's going to be feasible in the long run and that it's going to provide a proof test to do all of the appropriate testing, and it might be the first partial valve stroke test. So that leads me to look at the definition of what is the difference we mean between verification and validation. And certainly verification is the activities we've done, all of the looking at up front through the various stages and double checking, but the difference being that evidence is we're looking now in validation, the particular requirements for specific intended use. So we're going through function by function, activity by activity at verification and making sure everything is acceptable, that everything that happened upstream in the life cycle met the requirements, and that we have in place everything that we need to go downstream into the operating and maintenance phase. It's important to note that this validation is also, it ought to be one of the requirements for your pre-startup safety review for going through that safety gate before introducing hazards to the process. And validation may well be one of the contract markers for turnover from the construction contract to the operating team. Again, your functional safety management plan, this is a very important point to have in there because it can have not only safety implication, it's got contractual implication as well. The SIS Safety Validation Plan is probably going to be incorporated or become a part of your overall construction and commissioning and management plan. Clause 15 defines what the requirements are for that. I'm not going to sit here and read all of these to you. But basically, it's to give us that last safety check to make sure we're ready to put chemicals in the process and move on into those final phases. And here's a list of what the validation plan, this is not at all complete, you should look to the standards, but here's some of the more important variables that need to be included in that validation and testing plan. And of course we want to make sure that those plans that are written for testing the various activities are during normal and abnormal conditions. So when we're talking validation plans, we may have a validation or a site acceptance test plan just to do the logic solver, but then we're also going to want a plan to do the full SIF test as well. So there may be more than one document that goes into this. As we go into the operations and maintenance phase, the key activity through operations and maintenance is to test and maintain the system in such a way that we sustain the required safety integrity level. And of course, this is accomplished through the owner's procedures. There will be the proof test procedures that have been developed. They need to be executed on schedule, well documented, and then of course repairs have to be effected promptly in order to do that. So the functional safety management plan at a high level needs to point to these procedures. Who are the responsible parties, both departments and organizations, to be identified, and what are the competency requirements for those people? Here's some of the procedures and processes that would be part of the supporting document for the plan. Training, failure and fault handling, the auditing, the assessment, revision, and revalidation are very important parts of that plan, because if we don't audit, we don't follow through, then we don't know if we're missing key activities or missing the target. And there can be different maintenance plans based on the SIL level. So obviously if we've got something that's a SIL 3, we may have a more rigorous maintenance plan or more redundancy, you know, 2 sets of eyes instead of 1 set of eyes type practice for some of these. So there could be differences in what those requirements are. As we're going through and doing this periodic inspection and testing, then we are really looking for failures that are not revealed by the diagnostics. So there has to be our robust plan, what it includes in terms of the step-by-step test. But then we also want to go out and do the inspection, document what's found against that step-by-step test, who did it, when they did it, unique identifiers and tags for the field devices so we're sure we're doing it on the right device. And then consider a tool or have a provision for the tool where you're going to record all this information. And SIL-STAT is a good place to do that, because you can put the proof test procedures and do the actual documentation. And there's also equipment within that tools for helping to build the analysis of information over time so we can track the actual failure rates associated with components and know if we are achieving our targets. The modification phase, the main issue there is that if we have any modifications that are planned, you want to go through an appropriate management of change process. In essence, kick it back up to the appropriate location, usually starting again with hazards assessment, and start the life cycle all over again for those modifications, and make sure that the integrity is maintained throughout the entire modification phase and that we don't let any new risks slip in. Same thing is true for the decommissioning phase. We go back through management of change, make sure that everything remains operational during those decommissioning activities. And the two main reasons we may have decommissioning activities would be retiring one system to go into a new one, doing an upgrade, or if we've had change in our processes that have actually changed the risk profile and we find we don't need certain SIFs anymore. So that pretty much concludes the new material. I want to just kind of quickly go over a few slides from the first phase and just remind us what we're looking for on the Functional Safety Management Plan to kind of wrap this up. It is our roadmap. Basically, we anticipate a policy-level functional safety management plan that provides the overall viewpoint, but then also provides cross-reference for a related procedures, practices, plans, tools, anything that supports the objectives of that functional safety management plan. And whatever documentation or documentation method is required in order to maintain and have the information you've collected through this process where it can be easily analyzed and value can come out of collecting that data. Failure to have a functional safety management plan usually means things get missed throughout your construction design and construction scope, then they're not available or have to be developed last minute prior to going into operating. We also find there might be incorrect procurement. Wrong devices are purchased, so there has to be changes to correct all of that. And of course, if the verification methodology and the basis of the information that went into it is not supportive of your functional safety management plan, or if your plan doesn't call out what is required, then we'll find out things maybe don't meet the SIL targets. So we want to avoid these consequences of having to redesign, replace. We want to make sure that we have the ability to do proof tests, that everything that's there to get the proof test with the proof test coverage that is desired instead of something that might be limited by mechanical design. We don't want to have to replace sensors and final elements. But most importantly, the main goal is to make sure that the safety, integrity, and the function of the system meets the targets and reduces the risk within the process. And it does so throughout the entire operating life. Just one last quick look at a suggestion for how you might put this together. Again, I would recommend a functional safety management plan at the policy level that covers a number of the policy activities as described in Part 1 of the series. And then through Part 2 and Part 3, you should have gotten a sense of what we would want to say in the library of procedures, work instructions, forms, and records that would support the objectives of that policy. So with that said, this is our last slide. I'd like to point out to you some of the courses that exida has upcoming in the near future, next couple months, between now and the end of the year. And then if we'd like to hear your suggestions for webinar topics. So if you have any, please send it to us at academy@exida.com. Or if you have any comments on this question, academy@exida.com is another good place to send that. So I'm going to look over here to the questions list. Well, we got a quiet group this afternoon. Hi, thanks for very informative presentation. If we need a SIL2 SIF and there are 2 valves in series, 1 XV on-off valve and 1 control valve, final element voting is 1 out of 2. If we want to use certification versus prove it in use, does it need each valve to be certified SIL2 application, PFD average of 1 out of 2 voting, and the required range of the SIL? Basically, when we're talking about certifications, it is individual devices that get certified. Now, when you're doing your overall verification and looking at your total system, there may be non-certified components within the system, and that's where your verification calculation has to determine. But if you're looking at a SIL2 service, you've got 2 valves, and if one's on-off and one's a control valve, I would first question, is that control valve completely independent of the basic process control system? If it's not independent, there may be some issues with using it. But certainly those devices would have to be individually certified, and then through your calculations you would analyze if the overall system, because the certification of a device is simply saying that device is capable of achieving a certain SIL level if it's appropriately applied, appropriately installed, depending on what's going on with the system. Your actual SIL level is a function of the whole loop. So you're looking at the combined performance of all of the devices that go into that loop. Any webinar on calculation math basics? Yeah, basically, I think we've done a number of webinars where we have looked at that. That's a pretty extensive topic, and it doesn't fit real well into just 1 hour. I would encourage you to go out to the exida.com/webinar and just simply troll through some of those webinars to look at it. Another place you might consider is, I see a couple of them. This FSE 100 course is actually a 4-day activity, and it does a lot of looking at those calculations and details of the standard. It's really difficult to absorb the whole math basics in a very long seminar, but I will also look and see if I can point out some webinars that will do that math basics, and I will send that to you in an email. So pausing here, it looks like we are running out of time, and I don't see any more questions. So I want to thank you for your time and attention this afternoon. I do hope this webinar has been helpful in determining what you want to do for a functional safety management plan. And then if you have any questions, my email was included in the slides, my introduction slide, so you can follow up with those questions either with me or with Exida. Academy at exida.com, and we would be happy to follow up with everybody. So thank you again for your time and attention, and I hope everyone has a lovely day.